Kekmang. Okay. So before getting to graph theory, I will give a small introduction about mathematics. So you all know that mathematics is segregated into pure mathematics and also applied mathematics. So pure mathematics we cannot apply directly in our day-to-day life, but applied mathematics we can use in our day-to-day life. So graph theory comes under a discrete mathematics rather than a continuous one. So discrete mathematics helps to model pairwise relationship between the objects. So graph theory comes under a discrete mathematics, which is also an applied oriented mathematics. So you all know that applied mathematics is nothing but first converting the real life problem into a mathematical problem. So after converting the mathematical problem by applying a certain certain techniques, and we will solve that real life problem, right? So it is very complicated to analyze what are the techniques can be used to solve that problem. So before modeling that mathematical problem, we have to picturize. The real life situation can be picturized. Then it will be an easiest to form the mathematical problem, right? So it is a structure oriented, graph theory is nothing but a structure oriented subject. So now we will see the one by one. So the history of the origin of graph theory. So we will see the origin of graph theory. So the graph theory comes in a real life situation, arise from the real life situation by Leonhard Euler, Swiss mathematician in 1735. So there was a Pregel river in Germany. So there was a 4 land area. So to cross over each town, we have to cross the bridge, 7 bridges in that. The Pregel river, we have 7 bridges and 4 land areas. So to reach each and every town in that land area, they have to cross that bridge exactly once. So that is a problem. So this problem is still an open problem, which is not solved yet. But Euler have given a solution for this problem by structuring the graph like this. Is it audible? Yes. So here the Euler have given a solution for this problem by having that 4 land area as your vertices, and the connection between the land area is nothing but the bridges, 7 bridges. This is a solution given by a Leonhard Euler. So this is the main thing to arise the graph theory, right? So the first paper, as I said, the Euler was the first mathematician who given a solution for this problem. So he wrote the paper in 1735 in the history of graph theory. Next, the first book after Leonhard Euler, followed by the mathematician Koning, he gave the first textbook in Theodor der Enlichen and Unenlichen Graphen. That means that the theory of finite and infinite graphs. So in that book, he was written in 1936 in a German language. So now, the Sylvester was a first chemist who introduced the concept of graph theory in chemical molecules between the quantic invariance and covariance of algebra molecular diagrams. So he was the first mathematician who introduced in chemical graph theory. So now we come under the definition of graph theory. Graph theory is nothing but an ordered triple with a vertex set V of G. We will denote the vertex set by V of G, and E of G is nothing but the edge set. I of G is nothing but the incident map between the vertices and edges. So next, the definition of vertices. The vertices is nothing but the point. The points, or we can denote it as a node. We will say the vertices as node or point
that is nothing but the vertices. Then the line, the joining the 2 points, we use a line, so that is nothing but an edge. Edge is nothing but the elements we will denote it by E of G. This is an example. Here V1, V2, V3, V4 are the vertices of a graph, and connecting the vertices, any 2 vertices, we are using a line, that is nothing but edge. Here we have 8 edges in this graph. So here, as I said, V of G is nothing but the vertex set, that is V1, V2, V3, V4, and edges set we will denote it by E1, E2, etc., E8. So IG of E1, that means that E1 is incident between, this edge is incident between the vertices V1 and V2. Likewise, the E2, the incidency of that edge E2 between the vertex set V2 and V3. Likewise, we can map this vertices and edges. That means IG of E1, incident of that E1 between the vertex set V1 and V2. Likewise, IG of E2, V2 and V3, so on. Next, the n vertices. N vertices is nothing but a line, that means an edge which connects the, there is a connection between the 2 vertices. That vertices are called it as an n vertices. Here A and B are the n vertices for that edge. So then order and size of a graph. Here an order of a graph is nothing but the number of vertices in a graph. As we have seen in the previous example, there are 4 vertices. So the order of that graph is 4. So there is an 8 edges in that graph. So the size of the graph is 8. So we will denote the order by n and size by m. So n of G is nothing but 4 and m of G is nothing but 8 in the previous example. Next, adjacency. So adjacency is nothing but the edges are adjacent if they have the common n vertex. That means that E1 is incident with the vertex V1 and V2. So here V1 and V2 are the adjacent vertices because there is an edge between the 2 vertex. Right? So here V1 and V2 are adjacent by an edge E1. Likewise, there is an adjacency between V1 and V4 by an edge E4. Likewise, we can find the adjacency between the 2 vertices. Then incident. Incident is nothing but a vertex V1 is having an incident edges E1, E5, E4 and E7. That means that each vertex is incident by an edge. So here in the vertex V1 there are 4 incident edges. So likewise in V2 we have how many incident edges? E1, E7, E6, E2 and E8. Right? So these are the incident edges for the vertex V2. Then multiple edges. In this graph, a pair of edges incident to the same vertex set. That means that here B and C incident with 2 edges. These 2 vertex are incident with the 2 edges. That means here I didn't name it. So here I am having the 2 edges which have a common n vertex. So here we have a multiple edges. Then loop. In this graph, which is the multiple edges? E1 and E7, because E1 and E7 shares a common vertex V1 and V2. So that is a multiple edge. Then loop. Loop is nothing but an edge which starts and ends with the same vertex. That means here E8 is a loop which starts and ends with the vertex V2. Right? Next, neighbor. Here we are going to see about 2 neighbors, that is open neighborhood and closed neighborhood of a graph. So open neighborhood is nothing but here in a graph V1. V1 is neighboring vertices are which are all adjacent with V1. The vertices which are all adjacent with the vertex V1. Which are all the adjacent vertices? V2, V3 and V4. So these are all the neighboring vertex of that vertex V1, right? So V2, V3 and V4 are the open neighborhood for the vertex V1. If you include the V1 also along with the neighborhood, we can say that is a closed neighborhood of the graph. So we will denote n of V is an open neighborhood. N of closed V is nothing but the closed neighborhood of a vertex in a graph G. Simple graph. Simple graph is nothing but in a graph, if there is no multiple edge, as we have seen multiple edge and loop previous. So if there is no multiple edge and loop, then the graph is called it as a simple graph. So simple graph is simple if it has no loop and no multiple edges. This is an example for the simple graph. Then finite and infinite graph. As we all know that the finite set and infinite set. That means that finite number of elements in a set. Likewise, if there is a finite number of vertices and edges, then we call the graph as finite graph. Otherwise, we call that one as a infinite graph. Then the label graph. Label graph is nothing but just naming the vertices and edges. If the vertices are named by V1, V2, V3 and V4, these are all the labels for the vertices. E1, E2, E3 up to E8 are the labels for the edges. This is the labeling of a graph. Then isomorphism. So isomorphism, like an isomorphism of a function, the isomorphism of graph is nothing but we have to consider the two graph. We have to consider a two graph. If it preserve both adjacency in the graph, both the graph should preserve the adjacency. That means that here we have 5 vertices. In the second graph also it should have a 5 vertices. In this graph, if V1 and V2 are adjacent, in the next graph also V1 and V2 should be adjacent. So adjacency also preserve in the two graph. Then the graph is said to be the isomorphism of a graph. So here we can define that one as let G equal to V of G, E of G and Ig as per the definition of graph. Here H is another graph with vertex at V of H, E of H and IH be the two graph. And isomorphism, a graph isomorphism from G to H can be defined by the function pi and theta, where pi is nothing but the vertex set of the first graph to the vertex set of the second graph. Likewise, theta is a function for edge set E of G to E of H. With the property, what property we have to see? The adjacency should be preserved to both the graph, right? If Ig of E equal to U comma V, if and only if IH of theta of E equal to pi of U comma pi of V. That means that as I said, V1 is adjacent to V2. In the second graph also, it should preserve the adjacency between those two vertices, right? So this is an isomorphism of a graph. So this is a simple note from isomorphism of a graph. That is, the bijection pi satisfies the condition that U and V are n vertices of an edge E of G if and only if pi of U and pi of V are the n vertices, as I said before. Next, complete graph. So complete graph is nothing but all the vertices should be adjacent to each other. Each and every vertex should be adjacent to each other. For example, if I consider K2, here we have two vertices. Here N denotes the number of vertices. K2 means here we have two vertices. First vertex should be adjacent with second vertex and the second vertex should be adjacent with the first vertex. That is K2. Likewise K3, here we have three vertices. Each and every vertex to adjacent to each other. Here the first vertex is adjacent to the other two vertex. Likewise, each and every vertex should be adjacent to each other. This is nothing but the complete graph. These are some of the examples. We will denote the complete graph by a notation Kn. So this is a note from the complete graph. So to find the number of edges in a complete graph, we will use the formula n into n minus 1 by 2, right? So for a simple graph with n vertices, we have the size of the graph should exist between 0 and n into n minus 1 by 2. This is a result which we will use it in a research. Next, totally disconnected. Totally connected means graph according to the graph definition, vertex set cannot be an empty, right? So here, if the edge set is empty, then we call that one as a totally disconnected graph. There is no edges between the any vertices, right? So that is a totally disconnected graph. Next, a trivial graph. Trivial graph, there is only one vertex in a graph. Only a vertex. Only one vertex. We call that one as a trivial graph. We will denote that one as K1. Bipartite graph. First of all, a bipartite graph should be a simple graph. You all know what is a simple graph? No multiple edges and loops, right? So bipartite graph, first of all, a simple graph. First we have to partition that vertex set into two sets, right? So X set and Y set. Here I have taken a 7 vertices. Just I have partitioned into two set with 3 vertices as an X set and 4 vertices with the Y set. Each and every vertex of X should have an adjacency only with the set Y, not within the set X. Can you understand what I'm saying? So there is an adjacency between X and Y alone, not within a set X or within Y. Purinjada? Can you get the point? Yes. Is complete bipartite. Complete bipartite, like complete graph. What is a complete graph? All the vertices should be all the vertex should be adjacent with all other vertices. Each and every vertex should be adjacent with all other vertices, right? The same thing. First of all, a complete bipartite should be a bipartite graph. That means we have to divide the vertex set into two sets, X and Y. Each and every vertex of X should be adjacent with all the vertices of the set Y. Then each and every vertex of Y should be adjacent with all the vertices of X. That is a complete bipartite graph. There is a difference between the bipartite and complete bipartite graph. So we will denote that complete bipartite by the notation K, M, N. Here M denotes the number of vertices in the first set and N denotes the number of vertices in the second set. Next, complement. Complement is nothing but first I am considering a graph G. So whatever the adjacency preserved in graph G should not have an adjacency in the complement of that graph. If there is a no adjacency in this graph G, should have an adjacency in the complement of a graph G. Suppose if I consider these two vertices, there is an adjacency. So in the graph complement graph, there is no adjacency between those two vertices. Right? This is a complement of a graph. We will denote that one as G power C. It is a complement of a graph G. Next, this is a node. G complement, the whole complement is nothing but the original graph, because while taking the complement of a graph, if there is no adjacency in that graph, there will be an adjacency in the complement of a graph. If again I am taking the complement of that graph, again I will get the original graph. That is the G complement, the whole complement equal to G. Here the cardinality. Cardinality means the number of vertices in a vertex set is N, means the cardinality of E of G plus the cardinality of E of G complement should be the complete graph. Can you get my point? Because whatever the in graph, first graph, wherever there is no adjacency, there will be adjacency in G complement, right? So if I take the join of those two graphs, I will get the complete graph. So the complete graph edges, number of edges in a complete graph will be N into N minus 1 by 2. So that is the result. Next, self-complementary. Self-complementary is nothing but here a simple graph G is said to be a self-complement if G is isomorphic to G complement. So here I am considering the 4 vertices. In G complement also we will consider the 4 vertices, right? If the any 2 vertices of G is adjacent, while taking the complement, we should not have a adjacency between those 2 vertices. If I compare these 2 graphs, these 2 are isomorphic to each other. Am I right? So this is called it as a self-complement. Okay. Subgraph. Subgraph, as you all know, that the subset. So subset, what is a subset? a set which arises from a original set. Am I right? Subset is nothing but a set which arises from the original set. The same thing here I am considering a subgraph with certain number of vertices and edges from the original graph. That is nothing but a subgraph. From the previous example of that graph G, what I have taken with the multiple edges and loop, I have considered on previous example, right? From that, I have considered only the graph with the adjacency between those four vertices. So this is a subgraph of the graph G, right? So this is also a graph G. H is here a subgraph can be denoted by a H. So original graph will be denoted by G, then the subgraph will be denoted by H. Proper subgraph is nothing but the vertex set of the subgraph is not equal to the vertex set of the original graph, and also the edge set of the subgraph is not equal to the original edge set of a original graph, right? So if it is a graph, then the subgraph of this graph G is nothing but, here I have considered only the 4 vertices, but in the original graph we have how many vertices? 7 vertices, but I have considered only the 4 vertices, right? So this is the vertex set of H is not equal to vertex set of G, and also I have considered only the 4 edges, but in original graph we have how many edges? 8 edges. So I have considered only the 4 edges. So the condition satisfies. So we can say this is a proper sub. Here it induced subgraph. Induced subgraph is nothing but a graph which is induced from the original graph. So here I am considering the edge induced subgraph. Here A, B, C, D are the edges which I have taken from the original graph. So this edge induced subgraph which has been induced from the original graph. So we call that one as a induced subgraph. So here I am considering these 4 vertices from the original graph. So these 4 vertices which is induced from the original graph. So it is called a vertex induced subgraph or induced subgraph. Simply we call that one as a induced subgraph. Spanning subgraph. So as we have seen the proper subgraph, that is vertex set of H is not equal to vertex set of G. But in spanning subgraph, the vertex set of H and vertex set of G both are equal. Then the same number of vertices should be considered in a subgraph. But need not to be bothered about the edges. Then click. So click is nothing but a complete maximum subgraph is nothing but a click. So you all know that complete graph. What is a complete graph? Every vertex, each and every vertex should be adjacent with all other vertices. So in this graph, in that previous graph, what we have taken in as an example in previous graph. So here K4 is a click. K4, right? Wait, I will take that example. So suppose if I consider this one as a graph, here the induced, complete maximum subgraph is K4, because here we have K2, right? K2, then we have K3 and K4. So we have to choose only the maximum complete subgraph. So that is a click. That is in this graph we have K4 as a click. Yes. Next we are going to see about the deletion of vertices and edges in a graph. Suppose if I delete a vertex, if I delete any vertex in a graph, the edges which is incident with that vertex should also be removed, right? So that is a deletion of a vertex. If suppose the deletion of edges is nothing but, suppose if I want to delete any of the edges, so I can remove only the edge, there is no disturbance in the vertices, right? So these are an example for deletion of vertices and deletion of an edges in a graph. So degrees of vertices, which is very important. So the degrees of vertex is nothing but each and every vertex. The edges which is incident with that vertex is nothing but the number of degrees of a vertex. Here V1, we have 4 edges incident on it. So the degree of that V1 is 4. So the number of edges incident with that vertex is nothing but the degree of that vertex. So in this graph, the maximum and minimum degree of the, we have to find the maximum and minimum degree. Minimum degree is nothing but minimum number of edges incident in a vertex. Maximum degree is nothing but maximum number of edges incident in a vertex. So here tell me which is minimum degree. V1 have how many edges incident on it? 4. V4, 3. V3 and V2. Loop, you have to consider the loop with degree 2. So here V2 we have 6, 4, 5, 6, 6. So here the minimum degree is 3 and maximum degree is 6, not 4, 6. So V2 is the minimum degree. We will denote it by capital del of G, and minimum degree is 3. So we will denote it by small delta of G. Then K regular. Regular graph is nothing but what? All the degrees of the vertex should be same. So every complete graph is a regular graph, but every regular graph need not be a complete graph. We all know that well-known result, right? Then perfect matching. Perfect matching is nothing but spanning one regular subgraph. You all know that what is a spanning subgraph? The vertex set of H is equal to the vertex set of G. So one regular, that means that if I take a regular graph, if I take A and C alone, so here it is a one regular graph. If I consider only this part, so A and C have an adjacency. Likewise, if I consider B and D, it is one regular graph. Right. So the spanning one regular subgraph is nothing but a perfect matching of G. Isolated vertex, we all know that the degree is 0. A vertex with degree 0, we will call it as a isolated vertex. Then pendant vertex, using the degree concept, the degree, a vertex with degree 1, we call that one as a pendant vertex. So this is an example. Here the pendant vertex are, so E and D have a degree 1. So here the pendant vertex are E and D. Then degree sequence. So degree sequence is nothing but first you have to collect the degree of each vertices. Then you have to arrange it in an order, in certain order. That is called it as a degree sequence. First here for the vertex B, the degree is 3. Then for C, the degree is 5. Then for A, degree 2. Then for F, 2. Then for E, 1 and D, 1. So I have to arrange it in an order, either in ascending or descending. So first I will arrange it in an ascending order in this example. So E and D have the degree 1. So 1, 1. Then for A and F we have the degree 2. So 2, 2. Then for B and C we have degree 3 and 5. So 3, 5. So this is nothing but the degree sequence of the graph G. These are the theorems. We will see it in the next class.